Hello everyone, welcome to another GIS lecture video. And in this GIS lecture video, what I would like to do is talk about the idea of distortion. And with distortion, what ends up happening is that we have this issue where the map differs from the real world, right? So distortion is basically any way that a map differs from the real world. Right. And so there are all kinds of distortions that can happen in a map projection. But what I want to talk about is, at a fundamental level, why is there distortion? Right? What happens from a map projection perspective to cause distortion? And this goes back to the concept of what a map projection is, right? We have this idea that we have right? I'm going to draw this a little differently because I think it's a little bit easier to envision sort of horizontally rather than vertically, right? But that we have this idea of the, right, projection source. We have the reference globe. And then we have this developable surface. Let me make that a little bit better here. Let's go out like this. Why can I not seem to draw a straight line today? There we go. Right. We have our developable surface. Right, and what I mentioned before in one of the first videos was that this projection source, right, is projecting light from the projection source through the reference globe, right, onto the developable surface. Right, and that the whole point of the map projection was that you had a point on the reference globe being projected onto the developable surface. Right, and that a map simply was an accumulation of all of the points being projected from the projection source through the reference globe onto the developable surface. And what I said in that video briefly was that this causes the distortion, right? This conceptual construct, again, which is just a conceptual representation of the underlying framework of math, right? That these differences, I'm going to do this in orange, right? That these differences here, right? These are distortion. Let's make that a little bit cleaner by moving it down just a touch. Right, that these differences here, right, these are distortion. And the one place where the map projection touches where the developable surface touches the reference globe, right, this is called the standard line. Right, and the standard line is the most important part of map projections because the standard line is the only place. I'm going to highlight it. I'm going to make it a different color. I'm going to underline it, right? The standard line, or lines in the case of a secant projection, is /r the only place where there is no distortion. Where there is zero distortion, right? Underlined, italicized, do whatever you need to do. Standard lines are the only places on a map where there is zero distortion, right? I'm going to say that one more time. Standard lines are the only place on a map projection where there is zero distortion. Okay? So, now that we have this picture burned into our head, I want to compare this option here, which hopefully, without me telling you, you can see that there's only one point of intersection. So this would be the tangent case. Right, I told you, right? Tangent and secant cases, we're going to come back. This is where they come back, right? So what we can do is we can then also envision the same scenario, or as close to a scenario as I can redraw, right? Where instead of it hitting just once, instead it cuts through right? So now we have 2 points of tangency here and here. Wait, this would be the secant case. Right. So what makes the secant case different? Right. So if we, I guess we'll extend this out a little bit, right? If we draw the way that goes there, that goes there, 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 right? And again, the idea is the relationship between where the point is in the reference globe compared to where it is on the projection. So in this case, right, we have the same issue here that we had here, where the scale is enlarged. Right, so the difference between a point here and a point here is closer on the reference globe than the distances between here and here on the developable surface. But in the secant case, we have a second type, and I'll go and make this in pink, right? This area here, right? In this case, right, the reference, the developable surface is actually closer to the projection source than the reference globe. And in this case, right, you can imagine, you can actually see, right, that the scale is compressed. Meaning, right, that the light source is hitting the developable surface before the reference globe, meaning objects are actually closer together on the developable surface than they would be in the real world. So in this case, right, where the developable surface is outside the reference globe, everything is farther apart, things are bigger, things are aligned in a larger fashion, right? But if they're inside the developable surface, inside the reference globe, right, the scale is compressed. Things are closer together than they should be in the real world. Okay? So this is the fundamental concept of distortion. That you have areas where the projection source is projecting things farther apart because it's going through the reference globe onto the developable surface. In the secant case, you have areas where it's actually going through the developable surface before the reference globe, so things are closer together. And the only place you have no distortion, is where the developable surface and the reference globe touch, which are standard lines. And just to be clear, right, this is a standard line, and this is a standard line. Now, what I want to do is I want to end this video by recapping the three pieces we talked about in terms of how we categorize projections and how that relates to this idea of distortion, right? Because at the end of the day, the different classes, the different cases, the different aspects, those are all about moving around the developable surfaces, making them larger, making them smaller, changing how they're oriented, changing the shape, right? That's all that is doing, is that is changing the location of the standard lines so that the standard lines best fit with the area that you're trying to map. I'm actually going to make a note of that because it's very important. Right? Actually, let's make it a different color even. Right? Class, case, and aspect are all about moving the standard line to maximize the location of the standard line relative to the location being mapped. Let's try that again. Relative to the location being mapped. Let me repeat that. Class, case, and aspect, so the three properties of the map projections we've been talking about, the number one priority of those three knobs that we can tweak is all about moving the standard lines to maximize the location of the standard line relative to the location that's being mapped. Put another way, going back to our diagrams, right? The point of class, case, and aspect is to make it so that this red mark is as close as possible, or that these red marks are as close as possible to the areas being mapped, so that the distance or the difference between the developable surface and the reference globe is as small as possible over the areas that you care about. Let me say that one more time. The point of class, case, and aspect is to make it so that these standard lines are as close as possible to the areas being mapped, because we can change the shape, we can change the orientation, and we can squeeze the developable surface relative to the reference globe to try to place these standard lines as close to the area that you care about most as possible. Because again, right, standard lines are the only place where distortion is zero, and distortion gets progressively worse the farther away you are from a standard line. So, if you were trying to map Long Island, you would want a standard line to run along the length of Long Island, because that's going to give you the best possible map accuracy you can get. So as always, if there are any questions, please reach out. Thank you.